Okay, let's go with the dark energy. Okay, thank you, Nico. Okay, as already Nico said, dark energy was the winner between the battle between gravitational waves and dark energy. So let's explain what is this dark energy. What is the dark energy actually? Okay, what Nico's showing now is a very interesting picture. What you see on the top is a drawing actually of the Whirlpool galaxy M51. That was drew by Lord Rose in 1845. Actually, he looked at the eye, with his eyes to the using his telescope. I think that was in Ireland, as far as I remember, and he drew the Whirlpool galaxy. In that time, it didn't exist as photography as we have it today. It was in the beginning, so it's not used at all for scientific or astronomical purposes. And what you see down is the same galaxy taken by the Hubble Space Telescope. This was in the now in the 21st century, so it's about 170 years of difference between the two pictures, and also a ton of knowledge about the universe between both of them. Also, we have advanced a lot in the knowledge and in our understanding of the universe. The actual idea of the universe is very, very recent. Actually, at the beginning of the 20th century, we only knew one galaxy. That's our galaxy. We didn't know that were other galaxies like M51, actually, or the Andromeda galaxy. Actually, they were called spiral nebulas. People believe that there were nebulas in a spiral shape, but they were all inside of our galaxy. They were not outside. And it wasn't until the 1920s that we began to accept that there were other galaxies apart from our galaxy, the Milky Way. And the universe was much bigger than that we thought at the beginning. And in the next slides, you can see that this knowledge of the 20th century was followed also by the developing of the Einstein general relativity theory. All of you guys have heard about the Einstein general relativity, and basically what is based on general relativity, that is basically a modification of the Newton's gravity law, is based on the Einstein equations. This is not the typical equation that is E equals mass multiplied by the light velocity squared, but the ones that you see in the screen now, that's the Einstein equation. What you see is in the right, you see in that black box, the Einstein equation, you have some R's that actually what they measure, that is an approximation of the curvature of the space-time. And in the other side, you have this T that is called energy and momentum. That's basically everything that is the universe made. So if you can show the cartoon, Nico, in the right side,
yes.
You see cartoonish Einstein, and the beauty about this equation is that relates the mass, the content of the universe, and the energy of the universe with the space-time curvature that you had given by that R's. For that reason, it's beautiful. It looks kind of simple, but it's not that simple. Actually, that is a set of about 10 equations, and actually are something called differential equations that is kind of complicated. But anyway, even that is a oversimplification of the universe. Well, you can show the next slide. What you see in the next slide is, okay, you had Einstein thinking about that. Okay, the physics and the astronomers consider that this equation is beautiful. Well, we had a strange sense of what is beautiful or not, of beauty. But anyway, Einstein thought about this. Okay, I can use this equation to do predictions about the universe. You know, doing simplifications like the universe is homogeneous, uh, things like that is something called isotropic, so it's the same everywhere. So, but that means that he can solve this equation and do predictions. And he did some nice predictions. He predicted even if you have more mass, the space gets more curved. So that's a good thing. That's a important thing of the general relativity theory is that the mass produces a curvature in a in the space time. It's like if imagine like the space time is a blanket, you know, over your bed, and you put a ball there and an iron ball or whatever, or a baseball ball, then you see that the blanket stays curved, and this is the same that happens what with the space. But the problem that Einstein has also that this equation implies that the density of the universe, that means the amount of matter that the universe has, was equal to zero. That means that nothing exists in the universe, which is obviously wrong. I mean, you guys are here, I'm here also, and it's the air, the Milky Way, whatever, cannot be an empty space. So it doesn't have any sense. But well, Einstein was a very clever guy. You see it in the bottom there. He has an idea. Okay, say he was work it out in this equation, and he realized, okay, if I add a constant that you see this like a triangular shaped letter, that is a Greek letter called lambda, then the density, this means the amount of matter of the universe, is not equal to zero. So there is stuff in the universe, which is good, but the universe is static. So the universe doesn't expand, doesn't move, doesn't have a beginning, doesn't have an end. It's stayed the same. So if you see in the left part, what proposed Einstein was this constant called lambda that is closely related what is dark energy, and we are going to see further that. And he called it the cosmological constant. That's a beautiful name. That sounds like a very important. But implies that the universe never expands. No, it wasn't a beginning, nor an end. And people, you know, physics and astronomers were fine with that idea in that time. And talking about around 1920, 1970, 17. So actually this idea of a universe that has a beginning, that has an end, that it has a, you know, it's expands, was considered pseudoscience, so something like the flat earth now. So people did not believe in that. And then, so the idea, if you can see the next slide, is that the universe was static, you had galaxies on it, and these galaxies moves. You know, they can move in random waves, so that was fine. No Big Bang, everything stayed the same. No beginning, no ending. But it happens that appears this person with a, you know, smoking there. That's Edwin Hubble. That he was an astronomer, but actually also he was a boxer. The legend said that he was pretty good boxer. Actually, he managed to fight against the heavyweight champion on that time, and he managed to tie to him. So he was a tough guy. Oh, in Spanish, please. Sorry, I cannot do it in Spanish because it was last Friday. So, but you can see that in Instagram. I think that is recorded. No puedo hacerlo en español porque lo hice la semana pasada, pero esa charla ya está grabada y está disponible.
Está en IGTV, sí, exactamente.
Sí. I'm sorry, guys. So today is in English. What Hubble discovered in the next slide, uh, you can see what he realized. I mean, he was working in Mount Wilson, I think that's in California, and what he did is basically taking galaxies, see their color, and with the color, he measured the the distance, sorry, the velocity of the galaxies using the Doppler effect. I don't know if you guys knows about the Doppler
Just
effect.
1 second, I close the door, otherwise we'll have some noise. Sorry.
Don't worry. Uh, some technical difficulties, but okay, I'm going to continue in English again for this guys in Spanish. It's already in IGTV, so sorry for that. Okay, Nico is coming back.
Sorry, kids.
Don't worry about it. Okay.
Quarantines problems.
Um, okay, that's what you have there is the Hubble law. Let's understand what we have there. What Hubble did is basically observing galaxies and using this stuff called the Doppler effect. That is the same that you have when you listen to an ambulance. For example, if you have an ambulance that is coming, you hear the sounds that the siren of the ambulance does, and when the ambulance is coming, you hear that the pitch of the sounds get higher when it's approaching to you, but it's when it's getting away, is moving away, the pitch is getting more low. So in light, it says more or less the same effect, and it happens that if you see a light source that is coming towards you, the color gets bluer, but when it's moving away, the color gets redder. So you can know the velocity of the source if it's which is approaching or moving away. That's what Hubble did. He measures the colors, taking something called spectra, and he used a method for knowing the distance to the galaxies. And this method is called the Cepheids methods. Cepheids are stars, are pulsing stars, that the period of the pulsation is related to the how bright they are. So he knew how bright these pulsing stars in the galaxies. So he knew how far they were, and he measured with the Doppler effect the velocity that they were moving. What Hubble found actually, that is what you see in that plot, is as far, I mean, as farther a galaxy is, this faster it moves, and it becomes also redder. So if a galaxy is very far away from us, it moves faster, and another one that is more farther away, it moves faster, and all of them moves. All of them, they are moving away from us, all galaxies. So this actually what is called the Hubble law, that the velocity of the recession velocity, the velocity of a galaxy is moving away, is proportional to the distance. And that's proportional constant is called the Hubble constant. That is a very important parameter in the universe. And that's what this means. That's that the universe, or all the galaxies, are moving away from us, so the universe is expanding. But I already told you that Einstein believed that the universe was not expanding, was static. So this kills Einstein's idea. And actually, this was predicted and measured by physicist, I think Belgian, and his name was Georges Lemaitre. I think that's the pronunciation French, Nico? What are the French?
Georges Lemaitre.
Lemaitre. Okay, you can move you can pass the next slides. The next one. Okay, this is just an explanation of the. Oh, okay, and you had this person, Lemaitre, and well, he looks like a priest actually, a little bit. He has some glasses, but actually he was a priest, was a Catholic priest, So he knew that if he take Einstein's equations and he introduced the idea of an expanding universe, you can have a universe that has stuff on it, but it implies that it has a beginning. And to Lemaitre really likes that idea. There was something, I mean, that everything was at the beginning in one point, and then this point expands, and then he called the primavera, the 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 primigenian, or how do you pronounce it? Primaveral atom, the cosmic egg. Uh, so that was the idea of the Big Bang, and this his work really kills the Einstein idea. Um, you can pass the next slide. And so this is the idea of Lemaitre, more or less, that we have something called actually he never used the word Big Bang. He used this cosmic egg. Something happened in the beginning was this kind of explosion. Actually, it's not an explosion. It's the space and time itself that is creating and expanding. And then the stuff, the creation of the matter, galaxies, planets, and everything that we have now. Next slide. So Lemaitre basically discovered, with using the Hubble's findings, that the universe was expanding, and this killed this idea of a static universe that was Einstein idea. And this killed also this the cosmological constant idea that disappeared. And actually, legend said that Einstein said that it was his biggest blunder of his entire life. But it wasn't that a bad idea after all. And also, next slide, regarding this phrase that Einstein said, is actually you don't have to believe everything that you read on internet just because there's a picture with a quote next to it, and that's Abraham Lincoln and this meme I found it in the internet. And actually it's true, because in the next slide you see Mr. Einstein, okay, showing his tongue, because he never said that he was the biggest blunder of his life. That was actually another physicist, it was George Gamow, that say it. But actually what happened is that Einstein listened to Georges Lemaitre, and the legend said that he said that his mathematics was terrible, but his idea was fabulous. And actually he listened in a lecture from Lemaitre, and he stamped up and clapped, recognizing that Lemaitre was right. So he was a very humble guy anyway. Next slide. Well, this kills the idea of the cosmological constant. You say, well, where's the dark energy? Well, the dark energy is inside the cosmological constant. This idea of the expansion of the universe implies that the universe was in a hot state. And actually was predicted that that if the universe was in a very, very hot state at the beginning, it should have the radiation of the hot state can be observed now in the microwave regime as a microwave waves. And it happened in the 60s. There were two engineers for the Bell's Labs, for the Bell company, it was the telephone company at that time, Penzias and Wilson, and they were commissioned by the company to find some interference in the telephone calls. So the Bell company gave them this antenna that you see there, this kind of horn or weird thing, and they start to use it to find the cause of the interference in the telephone lines. And what did they find? They found basically that this interference was everywhere in the space, was coming from outside the air and was everywhere. And they realized that this was caused by the Big Bang, by by this hot state at the beginning of the universe, and that was called the cosmic microwave background. Actually, this was a no, it was not a proof, it was a proof actually. Sorry for the misspelling there. Of the of the of the creation of the universe. Ganesh Nane says, explain about this blue existent universe. What do you mean with the blue existent universe, Ganesh? Anyway, we can answer
Let's
questions.
continue on.
Yeah.
And
Okay. So next slide. And the good thing about this cosmic background radiation, that studying that you can know about features about the universe. And actually, what people found, that you had there maps, different maps of a patch of the cosmic background radiation. They found, first of all, that first of all, that the anisotropies, I mean the difference of temperature in this cosmic background were very small. They were very, 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 very small. It has almost the same temperature. What was the issue with that? The issue with that is that if everything has the same temperature, must be connected at the beginning of the universe. But if you allowed to do that, means that the universe at the beginning was expanding faster than the velocity of light, that light velocity, that which is somehow forbidden. So how can that happen? That's called the horizon problem. Sorry. And also, if you measure the shape of these anisotropies, you can estimate the amount of mass that the universe has per volume. That's called the density. And the density was that of the universe was a very special values, very close to a value that is called critical density. And what's important about this critical density? This critical density is the one, so the universe in a 4D space has a flat geometry. So the universe in 4 dimensions was flat. And that's called the flatness problem. And say, what? Why must be flat? If it's a little bit, if the density is a little bit high, the universe will be closer, like a sphere in 4D. And it was a little bit less, it's going to be like a saddle, you know, like a share that you see there. So, but it's not. It is just right. So that's something that we don't like too much. I mean, it's kind of, the universe was kind of fine tuned. So that's what's called the flatness problem. So we had to find a solution. And the solution was, okay, let's allow that the universe at the beginning expanded faster than the light. It's expanded faster than the light, and that's us allow it because it's not something moving inside the universe. Actually, it's the space itself that is expanding. It happens that you can sort out these issues, and this is called inflation. And for that, you need a cosmological constant that it has to live in the beginning of the universe, in the first seconds of the universe, and then dies away. But basically, we take back the idea of Einstein cosmological constant, and we use it to sort out these issues, the horizon problem and the flatness problem. So what happened next? Next slide, Nico. It happens that something that I call the return of the cosmological constant, and they're in Star Wars characters there. And that happens at the end of the 80s, or late 80s. The astronomers has the idea, okay, the universe is expanding, but can we measure if it's what is the acceleration of the expansion or deceleration? And that was important for the fate of the universe. So for that they use something called type 1a supernovae. That a supernovae is explosion of stars. The type 1a supernovae is a very special kind of explosion. Basically, you have a white dwarf that is the remaining of a low mass star. It's like the core of a low mass star, and these stars sometimes have a companion that is called a binary system. And it happens that the white dwarf, the small stars, start to, that is very dense, very compact, actually they're the size of the Earth, more or less. He start to feed from the material that the companion is formed. That's from a disk. And actually, when the amount of mass of this disk reach some critical value, it happens that they start nuclear reactions of that material, and the stars. And these explosions are very interesting because they can be used for measuring distance. They had some brightness that are related to how big is the explosion, and people can use it on standard candles, like using like the light post to know how far are galaxies. And actually, they were used for that. In the next slide, we see what is the idea. So this idea was actually carried out by some Chileans and American astronomers, Mario Muy, Jose Massa, Mark Felix, and Sam Sef from Tololo, Amuy and Massa from Universidad de Chile, Cerro Calán. And what the idea they have, okay, if you see in that plot, they will measure the redshift of the galaxy. That's mean how red the galaxies are. So that's mean the velocity of the galaxy, exactly like Hubble did. But instead of using cepheids for knowing the distance, they were using this supernovae type 1a, that because they're brighter, they can see for farther away. And they put it in this plot. And basically, if they wanted to find is as far as you are as far as you go, it's depend if the supernova gets fainter, that means that the universe is accelerating, or if it gets brighter, the universe actually is collapsing and is decelerating. So that was the idea, and they took the data, but the data was not they couldn't measure galaxies farther away enough to measure actually if the universe was accelerating or decelerating. But this was the base to another attempt that in the next slides you can see it. People from the US and knew about what they did, and they talked with them, and this was the base for a work of a group that called the High Set Supernovae Team. That was by Permuter, Schmidt, and Rees. And actually, they took the work that Amuy, Massa, Phillips, and Samset did. They used it as a base, and they did the same for galaxies that were much farther away. And they that are the red points that you see in that plot. Okay, sorry, I put the universo as the universe. Sorry, and it happens that all the points are toward the part that implies that the universe is accelerating. Okay, this could find, okay, the universe is accelerating. Why is accelerating? And that's That means that it's something that is making the universe to accelerate. And this was the return of the cosmological constant. Say, okay, let's put again the cosmological constant that Einstein proposed in 1917. This is now year 2000. And if they do that, they can explain this. But if you consider also the flatness problems that we said, that is about the amount of matter that has the universe, and you can show it in the next slides, Nico. In order to explain toward the left, in order to have that and have an accelerating, expanding universe, you can derive what are the compounds of the universe, and you find that only 5% is the universe is composed of only 5% of ordinary matter, the matter that we are made of, and that's what astronomer calls Bionic Matter. It's a just fancy name for saying ordinary matter. The 26% correspond to something that we call dark matter. Dark matter is basically the base of it gives the structure and support to galaxies, but it's only 26%. And the 69% that is given by the cosmological constant correspond to the energy of the cosmological constant. And this is what is called dark energy. So basically, the universe is filled in 69% of an energy that we don't know what it is. That's what we call it dark. And is making that the universe expands. So that is the bond of our actual comprehension of the universe, what we call the standard model. You can show it in the next slide, Nico. That is called in a fancy name like lambda CDM model or standard model, that we know that the beginning were some fluctuation of this energy in the vacuum. That is the Big Bang, and then the universe created and spun faster than the light. That is called inflation. So you solve the flatness problem and the horizon problem about 380,000 years after the Big Bang. The universe started to become it's not brighter, but it's less dense. So the radiation of the hot state start to emerge, and you can see it, and that is the born of the cosmic background radiation that we call. Then after a while, 400 million years, the first stars forms and the expansion continues. Galaxies, planets are created, and about 5,000 million years, dark energy start to accelerate the expansion. And that's our actual knowledge of the universe. But what we know about, okay, I will explain that later about the overlight speed, about a realistic or non-realistic concept. Okay. Thank you, TWFI. What we know about dark energy? First of all, we know that it's homogeneous with a low density. This is you can show that in the next slides, Nico. Here you have the ninja of the dark energy, because we don't know what it is, and we never see it coming, but it is there. And it's very homogeneous and a very, very low density. Basically, if you take a cubic meter of space in the universe, it would be only filled by 10 elevated to the power to the minus 27 kilograms of dark energy. That's very, very low. But it fills 69% of the universe. So the majority of the universe is made of this. Density is constant, so as the universe expands, it never dilutes, it never gets away. So this is very weird. That's what we know. Uh, Next slide. But then start that what we don't know. It could be something like a space property, that how energy, as a space expands, this energy, you know, ripping away, stretching away the universe. Some physicists believe that it maybe is a fixed force of the universe or a fifth component. So what are the fifth component, the fifth element of the universe? So what are they? I mean, first of all, matter, neutrinos, radiation, dark matter. That's the fourth components, and the fifth one will be something called quintessence. That is a beautiful term, but it's just a name. But actually, what we know, we really don't know. We don't have any proof about this quintessence. But something that we know is depending of the nature of the dark energy that is making the universe to accelerate. The fate of the universe is different. Next slide, Nico. We know that he has a strong role in the fate of the universe. Let's imagine that the universe continues to accelerating. As far as accelerates, we cannot see the entire universe. I mean, there is some limited amount of space that we can see, that is called the Hubble sphere. It's a limit of the observable universe. It happens that because it's accelerating faster and faster and faster, stuff that is in the border of this observable universe start to be away from us. So, and the universe is expand and expand more, and everything start to be away from our observable universe. So at the end, I mean, you ended up with a universe with only with the Milky Way. Then the borders of the Milky Way start to disappear. Then probably the borders of the solar system start to disappear, and the universe cannot form anything, and that's called the Big Freeze. And this will happen in something like 10 powers to 1,000 years is and 1 with 1,000 zero from in the future. So it's a long time. That's one possibility. Another possibility is that the expansion gets so faster and faster and faster and faster, so strong that the atoms itself rips away. They are destroyed, and that's called the big rip. And in some models, the big rip should occurs in 22,000 million years, 22 billion years in the future. So that's a lot of time in the future. And there's a third possibility that is called the Big Crunch. That is not about a sandwich from a fast food restaurant, but the Big Crunch actually is, let's suppose that the universe expands, but somehow the dark energy in the future start to getting diluted, becoming less important. And then it happens that you have another force, that is the gravity, that's, pull everything down, that gets together. So then gravity start to play a role, and it will stop the expansion of the universe. The expansion will reach the maximum, and then the universe start to shrink until a new beginning, until a small point. So then it will happen a new Big Bang, and the universe will reborn again. That's called cyclic universe. So that's the idea of the fate of the universe that we have now. And finally, next slide, Nico. All this knowledge is changing a lot. There is a work in that's published this year that is by Peche et al. And they were measure the Hubble constant. They remember this proportionality constant between how fast the galaxies were moving and the distance that they were. And what they found that using a method called of the water megamasers, they measured that the Hubble constant was 10% bigger than was predicted by the lambda CDM model. So it was a discrepancy. And this discrepancy means that the universe could be smaller, so the acceleration is not that big, and maybe dark energy is not that important. But they did it with a small amount of galaxies, so um, it's a suggested, it's a good suggestion, but it needs to better statistics to to be confirmed. But the take it out message here is that this is not written in stone, and we still understanding what dark energy it is. Actually, we don't know what it is, and we don't know also how important it is. So that's what wanted to tell you.